Andalusite is a rock-forming mineral that is mined for use in high-temperature refractories. Gem-quality specimens are cut into faceted gems and cabochons. Andalusite forms during the regional metamorphism of shale. It is found in schist and gneiss at some present in ancient convergent plate boundaries where the rocks have been exposed to the temperatures and pressures needed for its formation. In these rocks, Andalusite is often associated with kyanite and sillimanite. The minerals kyanite and sillimanite are polymorphs of Andalusite, each occurring under different temperature-pressure regimes and are therefore rarely found together in the same rock. Andalusite also forms during the contact metamorphism of shale. In this situation, it can form within the metamorphosed rock or in veins and cavities of the igneous rock causing the metamorphism. It can be associated with cordierite in hornfels, granite, and granitic pegmatite. Chiastolite is a variety of Andalusite mineral that contains black particles of graphite arranged in geometric patterns. The graphite is pushed aside by crystal growth within a rock that is being metamorphosed. As growth occurs, the particles become concentrated at crystal interfaces. The result can be a cross-shaped pattern within the mineral, similar to the cross stone shown in the accompanying photo. People have known about these minerals and cross stones for centuries and have valued them for their perceived religious or spiritual meaning. Attractive specimens are often cut and polished for use as amulets, charms, and novelty gems. Andalusite has a number of useful physical properties. It has the ability to withstand high temperatures without alteration. For that reason it is used to make high-temperature ceramics and refractories. The white porcelain of some spark plugs is made using Andalusite. Andalusite is one of a small number of minerals that commonly forms prismatic crystals with a square cross-section, see accompanying photo. This can be important information for identification in the field. People have known about these cross stones for centuries and have valued them for their perceived religious or spiritual meaning. Attractive specimens are often cut and polished for use as amulets, charms, and novelty gems. Transparent specimens of Andalusite are often strongly pleochroic. This makes them have different apparent colors when viewed from different directions. This pleochroic effect allows Andalusite to be cut into unique gemstones. It is a rock-forming minerals and is an aluminium nesosilicate minerals with the chemical formula Al2SiO5. At higher temperatures and pressures, Andalusite may convert to sillimanite. Andalusite is an aluminosilicate index mineral, providing clues to depth and pressures involved in producing the host rock. Although twinning is not common in Andalusite, nicely crystallized specimens that possess twinning can be distinctive. Twinning can produce cross-shaped structures perpendicular to the crystallographic C-axis, similar to what is shown in the rock in the accompanying photo. Andalusite, kyanite, and sillimanite all share the chemical composition of Al2SiO5. However, they have different crystal structures. Their crystal structure differs because they form under extremely different conditions of temperature and pressure. The phase diagram at left summarizes the conditions under which these minerals form. Andalusite is the low-temperature mineral of the three. Sillimanite is the high-temperature mineral, and kyanite forms at high pressures and lower temperatures. Information from a phase diagram can be useful during mineral exploration. If a geologist finds Andalusite in the field, the phase diagram reveals the possible range of temperatures and pressures that the rocks were subjected to when the Andalusite crystallized. If the mineral being sought has a dramatically different temperature and pressure of crystallization, then it might not be present in those rocks. If the pressure range of the target mineral is higher, then it is possible that it exists at depth. If the temperature range of the target mineral is higher, then exploration should move toward a heat source or toward greater depth. That is a simplified example of how the phase diagram can be used.